John Fullmer is a second-year PhD student in the Department of Earth and Space Sciences. His research investigates the modern formation of continental crust by volcanic activity. Please give a warm welcome to John.
All right, thank you for that warm welcome. As Juliana said, my name is John Fullmer. I am a second-year master's student at the University of Washington, currently studying volcanoes, but I really like to think of myself as a volcano plumber more than anything else. Because what I really like to look at are the plumbing systems of ancient volcanoes. I look to see how magma flows, how it's formed, and how it changes beneath the surface of the Earth. And although that's what I like to do, what I thought about presenting here for you guys tonight is rather on why we have volcanoes in the Pacific Northwest. Why do we have them here specifically as opposed to places like in LA in Southern California? And that's really what I want you to take home from this talk. So as you all know, in May 18th, 1980, Mount St. Helens blew. It was a catastrophic event that completely changed the landscape. It blew an eruption column that entirely blew off the upper 1/3 of the volcano and completely changed the topography. Along with this volcanic eruption, a large amount of material was blown out. If we want to look at the eruption column, it blew up material approximately 120 space needles high. If you want to put that into contrast, that's taller than any mountain in North America. It's a huge amount of material erupted out. The volume of debris that was left on the ground was even 2.5 space needles thick in some areas. This is a huge amount of material coming out of a single eruption. Now, to put that in perspective again, I've put I've got a volume here of Lake Washington, which is approximately 3 cubic kilometers. So if you were to take all the water from Lake Washington next to us and put it into a giant cup, it would be 3 cubic kilometers. Mount St. Helens is approximately 1/3 of that, represented by the small red dot. It is considered a relatively small eruption on the volcanic scale. For another example, we have Mount Pinatubo, which erupted in 1991 in the Philippines. That blew 10 times the amount of material into the air as Mount St. Helens. So this was a much bigger eruption. It was a big eruption by most standards, but it still wasn't even the biggest eruption that we have in historical time. Going back even further, we have the eruption of Tambora in Indonesia. 1815, it blew 100 times more material into the sky than Mount St. Helens did in 1980. And the incredible thing about this is it actually changed the climate at the time. The following year was known as the year without a summer. That's how drastic this eruption was. And so even though we consider Mount St. Helens to be a catastrophic event or a large eruption that changed the Pacific Northwest, it's kind of important to put this into context that there are other volcanic eruptions that are oftentimes considerably larger and more eruptive. And so there's a few things I want you to consider about this. How does magma form? How do we produce all this magma, all this material that needs to erupt out to the surface? There has to be some ability to produce 100 cubic kilometers of magma to erupt out. And that's not even all of the magma. In fact, it's only a small portion of the total magma produced. Most of it actually stays within inside the Earth. The other thing I want you to consider is what causes magma to erupt in the first place. You can't just have a magma and then force it to the surface. There has to be some process by which it's able to explode or erupt out, often in a violent manner. And the last thing I want you to consider is what happens to all the magma that doesn't actually erupt. What happens to all the magma that stays within the Earth deep down? Does it just disappear? I mean, it's the majority of the magma out there, and it's an important thing for us to remember. But out of all of these things to consider tonight, please take home this one key message of why does the Pacific Northwest have volcanoes? And that's what I'm going to talk to you about right now. But before I do, I want to just go back to a basic geologic concept of plate tectonics. So the way I think of plate tectonics is a lot like an eggshell, where you have the outside of the shell, which is made up of a solid, rigid body that is often fragmented into a series of plates. And these plates might move against each other or together. And that's the same sort of thing that we have on the exterior of the Earth, where you have a bunch of different plates shattered on this rigid body that are moving against each other. Now, these movements are actually pretty small. Plates only move about the speed our fingernails grow. So this is a really slow process, but yet its implications are actually tremendous for what it does in shaping our landscapes and forming our planet. Unlike an eggshell, the Earth actually has two different kinds of plates. You have oceanic plates, and then you have continental plates, and they're physically different. Oceanic plates are made up of a rock called a basalt, which is much, much heavier than the continental rocks, which are made up of andesite. And so if you were to put these on the scale together, the basaltic oceanic rocks are going to sink to the bottom, and the continental rocks are going to rise to the surface. And so this is an important concept moving forward. But what does this have to do with Mount St. Helens? What does this have to do with volcanoes? Well, if we zoom out from Mount St. Helens here and its erupted north flank, and we go to the state of Washington, here's Mount St. Helens for scale, and then we zoom out to the Pacific Northwest on Google Earth, we can actually see the outlines of these plates. So right here, I have the outline of a plate, and off to the west here, we have the oceanic plate with its very dense oceanic rocks, and off to the east, we have these lighter weight continental rocks. And if we look at the motion of these plates against each other, the oceanic plate is moving eastward, and the continental plate is moving westward. So something's got to give when you have these two large masses of rock colliding, and as you might expect, the denser, heavier oceanic rock is actually going to sink down beneath the lighter continental rock. And that's the basis, the beginning for forming our magmas that we have. So here's a wonderful animation created by Tanya Atwater at the University of California in Santa Barbara. And this shows a cross-section through the Pacific Northwest of what's kind of happening below us. So over here to the west, we have the oceanic plate moving in, and over here to the east, we have the continental plate. And what's happening is this oceanic plate is being brought down to depth. It's forming a magma, which rises to the surface and then erupts to form our volcanoes. But I want to go into these processes in a little bit more detail so that you have an idea of the plumbing that goes on. So I want to focus on this process first. What's going on here that forms a magma? How do you give birth to a magma? Well, if you have a rock deep down in the earth and you heat it up, you start cooking it, you don't actually form a magma. Okay, so that means we don't naturally have a magma. Something needs to happen. We need to add an ingredient in order to form a magma. So if we take our oceanic rock, and as you can see here, it's very porous. It has a lot of holes in it, it's got a lot of water filling those holes, and it also has minerals that store a lot of water in it. And if we were to bring that down to depth, bring it down a bunch of kilometers, we're gonna be pressing on it. It's like putting it into a vice grip. We're gonna be squeezing the crap out of that rock. And as we're doing that, we're also heating it. The further we go down into Earth, the hotter it gets. And so we're squeezing this rock and we're heating it up. And as we do that, we squeeze out a bunch of water. This water might be coming from the pore spaces, it might be coming from minerals breaking down, and it is released into the overlying rocks, and it comes out. And so this water actually plays a tremendous role in the formation of volcanoes, and in fact, in giving birth to a magma. So, as I said before, if you have these deep rocks and you start cooking them, you don't get a magma. But if you have these deep rocks, and then you heat them up, you start cooking them, and add a special ingredient of water, you reduce the melting temperature far enough to where you're actually able to produce a magma. And so we can give birth to a magma at depth. And you can think of this kind of like if you have a iced over sidewalk. It's not something that you might get in Seattle very often, but back home in Salt Lake City, this was a common occurrence. And you would salt that sidewalk, and by doing so, you reduce the melting temperature of the ice, thus allowing it to melt. And this is kind of how I think of the melting of the lower Earth. So we take our oceanic rocks, we bring them down to depth, we squeeze them, we cook them, we take the water out, reduces the melting temperature of those rocks that are deep down in the Earth, and we form a magma. So we've officially given birth to our first magma. But what causes a magma then to rise towards the surface? Do all magmas rise? Not necessarily. It's really a function of the density. It's kind of like this beaker of water and oil. The lighter, less dense oil will rise up to the surface, whereas the heavier water will actually stay behind. And so only lighter weight or less dense magmas will actually rise. And the key component to consider here is that this density really depends on the composition of the magma. But how do you change a magma's density? How can you make a magma change to become less dense so that it rises? Well, one way you can do that is through crystallization. So if you have your magma body sitting down deep within the Earth, you're going to have a lot of heat going away from this magma into the surrounding wall. And as this heat dissipates into the surrounding wall, it's going to cool the magma off. As you cool the magma, crystals will begin to form. Well, these crystals preferentially take in heavy elements such as iron and titanium, and they'll bring them into their structure and remove them from the liquid melt. When they do that, the melt is removed or depleted in these iron and titanium elements and changes to a lighter and less dense magma. Now, this will happen progressively as more and more crystals form. You get a lighter and lighter composition the more crystals you have. Eventually, these heavier minerals, rich in these iron, magnesium, and titanium, will sink to the bottom, and the remaining liquid will flow upwards, and you're left with a less dense magma that is then able to rise, much like oil and water. Another way that you can produce a less dense magma and get it to rise is you can melt surrounding rocks. So if you have your magma body again, and you were to dump in a bunch of rocks that were surrounding it, those rocks are going to get melted, as you might imagine. So heat from the surrounding magma is going to go into those rocks, start melting away at them, and let's say these rocks are very rich in lighter elements, such as potassium and sodium. As that rock melts, the potassium and sodium are going to be able to leave from that rock and go into the surrounding melt. And so we're able to change the composition of the magma, not by removing something this time, but rather by adding these lighter elements and making it less dense. So the cool thing about melting these surrounding rocks is when we do it, we're actually removing energy from the magma and causing it to cool, which simultaneously creates crystals. So when we're melting something, we're also cooling the magma, crystallizing it, and further changing composition to something that's less dense and also wants to rise up. So these processes need to take place before the magma can rise. The last of these processes that I wanted to mention is that magmas can mix. You could have a heavy magma and a light magma that could come together and mix to form a new composition. Now, this doesn't always happen, and in fact, it can be very difficult for this to happen, but if you were to have a large body of magma that was very heavy, very young, very rich in those iron and titanium elements, and a light magma come together, you then form a mixed magma in whatever proportion that can then rise towards the surface. But which of these magmas rise? Well, as I already said, the heavier elements are going to be more dense. So the iron and titanium rich magmas in crystals are going to sink, and magmas that have potassium and sodium or other light elements are then going to rise up towards the surface. So let's say we have our light magma sitting down deep beneath the Cascades, and it's going to start rising as it changes through crystallization or through melting of the surrounding rocks. And as it does that, you're going to be effectively removing the rocks that were originally sitting over top of it. It's now higher up, and so there's fewer rocks sitting over top of it that are pressing down on that magma. So what that's going to do is it's going to allow all the vapors within that magma to start forming. And these are going to grow and grow the closer you get to the surface. And so underneath some of these Cascade volcanoes, you're going to start letting these bubbles expand. And as they keep expanding, they're going to be exerting a pressure onto the surrounding wall rock, right? So these bubbles need to go somewhere. They're going to build up all this pressure, kind of like you take a Coke bottle and you start shaking it and you start shaking it, but you're not increasing the space. We all know it's going to happen. There's going to be a buildup of pressure until, boom, we've got our eruption. You're going to coalesce all these bubbles together, they're going to unite, and they're going to form in a catastrophic eruption or a large-scale eruption of any case. And so you could just think of this as releasing the cap on that Coke bottle. All the material comes out, you release all those gases into the air, and that's what we had with Mount St. Helens, or what we could have with Mount Rainier out here. Here's a beautiful picture taken by the United States Geologic Survey of the Mount St. Helens eruption. But, okay, so we've had a magma erupt, but what happens to the magma that stays within the Earth? That's the majority of the magma in the first place, right? Well, that magma is going to keep cooling. Crystals are going to keep forming. The crystals that already existed are going to start expanding. So heat from the magma is going to be released into the surrounding rock. It's going to cause the liquid to start cooling, and these crystals are going to grow and be left behind deep down in the Earth. So we bring down our oceanic rocks, we cook them, we pressure them, water pops out, and we melt the deep earth rocks. That magma is then going to rise into the continents. And when we do that, we're actually adding more and more material into the continent. And so what the continent's going to do is it's going to grow. It's going to be expanding in size. And so we're actually building continents in a sense when we're adding magma to them. But there's other forces at play here too. There's going to be erosion. There's going to be rivers and glaciers. We've all seen the tops of all of our cascades. They're covered in ice. They're going to be eroding down. Rivers are cutting through them. And then there's also going to be the sinking process, where rocks that are forming from those really dense, really heavy crystals deep down in the continents are eventually going to fall off or sink back down deep into the earth because they're more dense. And so it kind of brings forth the question, you know, are we actually building continents? Are they actually growing? We're adding more material, but how much are we removing? And these are some of the questions that I like to think about in my research. So before I wrap things up, I just want to reemphasize the point of why we have volcanoes here in the Pacific Northwest. It comes back down to this idea of plate tectonics, this idea of these eggshells moving against each other, where you have the heavy oceanic rocks colliding against the lighter weight continental rocks. The oceanic rocks are going to be brought down far into the earth, where you're going to pressure them, you're going to squeeze the water out of them. Water's going to be released, forming a magma, which then will change either through crystallization, melting of surrounding rocks, or perhaps even mixing. It could even be all three of those. Then it rises towards the surface where it pools, much of which the magma erupts when the bubbles coalesce. Some of it stays down in the earth to help build continents, or at least continue a supply to the continents. And there we have our volcanoes, our cascades, just like Mount St. Helens. With that, I'd like to thank everyone for coming out. I want to thank Engage for giving me this opportunity. I want to thank the College of the Environment, University of Washington's Earth and Space Science Department, Town Hall for letting me be here, and of course all of you for coming out to listen to me talk. Thank you. Yeah, questions?
So, how are the Olympics formed then?
How are the Olympics formed?
That's not volcano, right?
No, it's not.
You didn't have it on there, you said the Cascade.
Right, so what's happening is that's actually kind of what happens when you squish up all these continental rocks together. When you're pressuring them together, you actually form a bunch of folds, and you deform the structure of those rocks together to get kind of a little a mountain range before the volcanic mountain range, and that's a pretty common thing.
So there's other places in the world that have like little Olympics too?
Mm-hmm.
Close to the ocean or whatever?
Yeah, it definitely happens. There's a lot of coastal ranges and things like that.
Is that probably down there South America?
Yeah, so there's a coastal range, and then there's the Andes volcanic mountains too. Mm-hmm. Yeah.
The idea that a molten material, even when it's light, is able to rise up through the rock which overlies it is a bit counterintuitive. Can you say a little bit more about the processes that allow that to happen?
Yeah, you're right. It's definitely not as simple as those pictures made it look. You're going to have some sort of fracture. You can't actually melt magma can't melt its way to the surface. It's going to cool off too much, and it'll never reach the surface. So you have to have some fracture system or some breakage of rock, some pore space for that magma to actually move through. Luckily, in a lot of these tectonic environments where you have two plates coming together, there's a lot of fractures in the rock. And so it actually allows that magma to rise through those fractures pretty easily. There's also pore space for them to go.
Okay, so there's that process doesn't bear much relationship to the idea of convection in the mantle.
Right.
I'm sorry.
So, sorry, I don't understand the question though.
The process which occurs up in the crust here,
Mm-hmm.
the fracturing that allows the lighter magma to move toward the surface, then has no particular relationship to the concept of convection in the mantle, where the mantle material is, in some sense, semi-fluid, or whatever the term is for it.
It's
There's motion of material in the mantle.
Right, so the mantle is a solid for the most part, and it is a viscous solid, so it's actually deforming. It's kind of like a plastic that's moving around. And then when we're melting the mantle, so that's those deep earth rocks I talked about, That's when you add the water to it and you melt it and you form a magma, which is then going to have to rise through some sort of fracture system or through the pore space created when you melt that rock in the first place. You're going to create a void, and then it's going to pool beneath the continents, and it's going to have to change in composition somehow to continue rising up, either through crystallization or melting. Crystallization is probably going to be the biggest component there. And then you're right, it's going to have to find some system of fractures, some network that's going to be created either from melting some rocks by pre-existing magma or through some sort of tectonic breakage where you have these open spaces for the magma to flow up.
Thank you.
Yeah, go.
What is the professional speculation about the effect of a slippage of the San Juan Fuga plate that would lead to, let's say, an 8.5 to 9.5 earthquake on the magma under Mount Rainier?
Wow, that's a good question. I don't honestly know. Shelley back there actually studies these earthquakes in this area. I don't know if you have an answer for that.
You can talk to me after his talk. I'll be happy to talk.
Okay, I don't know. That's a great question, though.
So I had a question about how they measure the volume of eruptive material that comes out of these volcanoes. And I noticed that, the ones that you presented were from the 1800s up until the late 1900s, around there. I was wondering if the methods that they use are comparable when they're measuring those volumes that are erupted as well.
Between the older eruptions and like Mount St. Helens, which was fairly recent?
Right, yeah.
Okay, yeah, so how do we measure those? Well, all that material is left behind, right? So it erupts out and it's either left behind as ash particles that fly away or as nearby pyroclastic flow deposits. So that's all the material from the eruptive column that gravitationally collapses down the side of the mountain. And that forms these large deposits, or these 2.5 space needle thick deposits that we can go back and measure. And we kind of measure it in an area and kind of do some extrapolation to try to figure out what that is. And then when you're going back far enough to, let's say, the Tambora eruption, you're going to have to think about erosion and how that's playing a role. And so people actually have done studies for the erosion rates and then try to add that material back on to what used to be there. Yeah. Paige.
Okay, I imagine it's fairly variable, but is there some sort of time scale between your birthing of your magma and it potentially rising to the surface where it could potentially become a volcano?
Yeah, that's a good question. What's the time scale for this? It's a really good question, and it's one that's actually being looked at right now in our lab. There's been some recent dates of a system like this growing, and we see that it's growing in a relatively short period of time geologically of several millions of years, tens of millions of years. So that's geologically a short period of time, but there have been other places that they think it's a longer period of time. And so it's not happening in, you're not forming a magma and it's not deep down in the earth and it's not rising immediately to the surface. It's a prolonged period where you form a magma that rises a little bit and it makes the next little bit easier to grow up. It makes, it heats the rocks around it, it creates fractures and allows more and more magma then to rise to the surface later on. Camille.
What depth do you start producing magma? Like when does it actually start melting? Like what's the depth?
Yeah, that's a great question. It really depends on where you start releasing water. So that's going to happen at various depths because different minerals will break down and release water at various depths. And that's really a function of the pressure, right? To give you a specific depth, I can't off the top of my head. I'd have to look that up.
Like hundreds of kilometers or?
I don't think so far. I would guess more on the scale of 10s to 50 kilometers down. But I don't know an exact number off the top of my head, but that seems like an appropriate range. Mm-hmm.
So why are the volcano formation such a localized phenomenon? One could imagine that this process of magma formation and birth could happen anywhere along the interface. So why are they spatially sort of clustered or sporadic as opposed to everywhere along the subduction?
Yeah, so why do we have volcanoes localized in an area and not extended along the entire subduction zone?
Sure.
Is that your question?
Yeah.
You do have them across most of the subduction zone. If you go back to if I go back to the subduction zone here, this oceanic plate actually ends about in California, kind of over by Shasta. And so there's a kind of a continuous range of volcanoes from Mount Shasta all the way up into Alaska where this process is taking place of this oceanic crust going down. And a good example too would be like the Andes down in South America. It's kind of the archetype of this happening where you have an entire mountain range spanning most of a continent, all forming these mountain chains. Does that answer your question? Or are you thinking like, why don't you have volcano next to volcano really close?
Exactly. Why are they not more dense along the subduction line?
Mm-hmm. Yeah, that's a really good question. I think it would have to go back more to where magma can rise and where it's easy for that magma to rise. So there has to be these fractures pre-existing there. You also, when you have a magma in an area already, you need to, that heats up the surrounding rocks and makes it easier and preferential even for more magma to come to that same region. So both kind of a mixture of, it has the volume available, it's an easy pathway, and it's a warm pathway, which is, magma wants to go with those warmer pathways. It's just easier for it.
I was impressed with your animation, and I noticed it comes from UC Santa Barbara.
Yeah.
Is there much cooperation between the departments of up and down the coast?
There is, depending on the specific research going on. Between me and Tanya Atwater, there is absolutely none. She's created a bunch of really fascinating animations similar to this, simply for educational purposes, both for teaching her classes as well as other classes. And so these are free to give out and distribute. And so it's just for general education that she does this. But I've worked with other people from different universities, specifically the University of Nevada, Reno. We went down to Argentina last year to look at some rocks together, some kind of an ancient system of this, ancient plumbing system of volcanoes. And so there is definitely collaboration between universities.
The whole Andes are a crumpling up of plates, right?
That would be more the coastal range, would be the crumpling up, whereas the Andes themselves proper would be these volcanoes, this chain of volcanoes running along.
So seeing next week is 35 years since Mount St. Helens, and there's some of us who remember it. I mean,
yeah.
You probably weren't like that.
Nope.
What's long term on that? Is it going to basically do it again? I mean, because it did it in the 1800s, so it's projected to do it.
Yeah, I mean, I don't know what's going to happen with the volcano. I do know.
It's the most studied one ever, though.
It's actively growing now. I mean, it's still forming these lava tubes, or not lava tubes, these lava domes up at the surface, and it's an actively growing mountain, and it's been actually very active recently seismically. It's had a few smaller eruptions, specifically around 2006. Those have mostly been water-based eruptions. And it's erupted quite a bit over the past few hundred years, so it's not unreasonable to think that it would happen again within the next 100 years or so.
Would there be talk then that knowing it's going to erupt to just basically blow off its top so it allows the pressure to be released? Have you ever really thought about that?
I haven't thought into the hazard assessment of it. I don't think there's the funding there yet, but...
Well, we have quite a few bombs we can try.
Would be a fun experiment in any case. All right, I think I have to cut it short on the questions, but if you have any more questions, I encourage you to come talk to me afterwards. Thank you very much.